Example 3. So at what values of x in the open interval does that function have a relative maximum? Okay, so remember last class we learned about functions defined as integrals. So this is just the equation for h of x, right? So don't get bogged down on it being defined as an integral when you're asked about a relative maximum. Remember, when you see that, just stop, ignore the problem, and just write down what it means for f to have or h to have a relative maximum. Okay, and then it does say use your calculator, so you do need to get your calculators out while we do this. Okay, so to have a relative maximum, so remember I like to justify first because then that tells you what you're looking for. So h of x has a relative max when what?
H prime goes from positive.
When h prime of x changes from positive to negative. And so this is the number line analysis, okay? So we need to find, just like we did in Unit 1, we need to find h prime. Now we look at the function of h, and we're finding h prime. So now that I see h is a function defined by an integral, if I'm taking the derivative of an integral, that's the second fundamental theorem of calculus. So as a review, the second fundamental theorem of calculus states, if I take the derivative of an integral, where I have a variable sitting in one of my limits of integration, then you take your function, you evaluate at your upper limit times the derivative of the upper limit, minus evaluate at your lower limit times the derivative of the lower limit. Does everyone remember that? That's the second fundamental theorem of calculus. Okay, so now I'm going to do that. So sine of, so I don't need to know the integral of sine of t squared. Okay, you're just going to say that's going to be sine of 2x squared. So be careful there because that's actually going to end up being 4x squared times the derivative of 2x is 2, and then minus the bottom limit is a constant, and the derivative of that is 0. So I want you to think about that, but we don't have to write that down. Minus 0. Okay, and so that is our derivative. Let's clean that up. So we get 2 sine of 4x squared. And then the function's asking for when, or this question's asking for when h prime changes from positive to negative. So this is where we would use a calculator, and we would plug this into the calculator. So let's do that. Correct. Yeah, so you want to zoom in first before you can, yeah. So 2 sine of 4x squared. Okay, and then we're going to zoom in. And I never use zoom. I change my window settings. So I'm going to change my window settings from 0 to 2. And that's much better. And so now I want to find where this graph crosses from positive to negative. So we're going to analyze the graph, find zeros. So I see my first one right there at 0.86. Oh, not a minimum. Oh my goodness. Then here. And then there's actually, so this is the danger of just going from 0 to 2. So you can see here that actually crosses as well. So sometimes it might be nice to go on either end of 0 to 2, just so you can see and make sure, because there's actually 3 places where this does that. Keep hitting the wrong button. Okay. So those 3 x values are where the derivative changes from positive to negative. So that's where h would have relative maximums. So that's at, so this occurs at x equals 0.886, 1.535, and 1.772. All right, example 4, find this derivative. Okay, find the derivative of g of x. And so this is one where I have a variable or a function of x in both the upper limit and the lower limit. Okay, so if I'm finding g prime of the integral, we don't have to integrate that. We're just going to evaluate 1 over t at x squared, then times the derivative of x squared, minus evaluate at 3x times the derivative of 3x. This actually does a kind of cool thing. So when that cancels out, you get 2 over x minus 1 over x, which ends up being 1 over x. That does not always occur. It's just the nature of this problem that it ended up being 1 over x. Okay, that doesn't always happen. So at what values of x do relative extrema occur on that? And so now I want you to try this one on your own. So similar to example 3, and no calculator on this one. So do this one on your own, and then when you're done, you can look up. All right, so next, so there's a lot of these types of questions. Example 6 is a free response question from a past AP test, and you have a lot of those same types of questions on the 2.5 problem set. So notice that we've got the graph of f, and so you're like guaranteed to have free response question over this. All right, it's every year. So we have g of x is defined as the integral from 1 to x. I want you to think of, remember when you're taking an integral as accumulation of area, all right? And so if I am defined from 1 to x, then I'm starting to accumulate at, if you want to think of this time, at time 1. Okay, so if I wanted to calculate, for instance, g of 0, yes, okay, so g of 0, so when I'm going to plug in 0, I'm actually going to be accumulating area backwards, all right? So remember that property. So if I go in and I plug in g of 0, just like a normal evaluation of a function, you're going to replace every x that you see with 0. X, not the t value. So if g of x is defined as the integral from 1 to x, I'm going to replace x with 0. And so what that means is that's actually the negative, right, of that property. Since 1 is bigger than 0, that's the negative of the integral from 0 to 1 of f. Okay, because it's like I'm accumulating backwards. All right, so the integral from 0 to 1, that area is positive area, but then we're going to negate it because of the property, since we're defined as starting at 1. Okay, so then we want to find the negative of that area. Anybody find that area? 3 halves, correct. So g of 0 would be negative 3 halves. Okay, so now that we're taking derivatives again, we're obviously answering all these old questions from unit 1 and then also before then. So now we're asked to find the equation of a tangent line. All right, so equation of a tangent line, you need 2 things. You need a point and a slope. As soon as I see tangent line, I do that. I would need a point and a slope. Okay, so they give me at g of 1, so the point would be g of 1, right? Okay, that would be the y value of the point. And then the slope would be what? G prime of 1. Okay, so g of 1, we have the equation for g, so we're going to go ahead and plug in 1 for x. So we get the integral from 1 to 1 of f, and that's really easy. We just get 0. So the y value of my point is 0. So I have the point 1, 0. Good? Now, the slope, I need to calculate the derivative of g at 1. But before I can calculate the derivative, I need to know what the derivative is. So then we just take the derivative of g, just like we did in the previous examples, and we apply the second fundamental theorem of calculus. So this is a really basic one. So what is the derivative of g? Simply what? Not f prime, just f of x. Okay, so g prime is equal to f. Okay, so then g prime of 1 is equal to f of 1, and that's just the point on the graph of f at 1, which is 1. Everybody clear on that? So now we write the equation of our tangent line. Y minus my y value of 0 equals 1 times x minus 1. You can leave it like that, or you can just say y equals x minus 1. It doesn't matter. Good? Questions? All right. Find all relative extrema. So we've gotten practice with that, so let's try that now. So relative extrema is when g prime, which equals f, is equal to 0. You need to state the g prime equals f piece. Okay, so we have relative extrema at g prime, which equals f, when it's equal to 0. And that occurs when? When is f equal to 0? At x equals 2. F is 0. Correct? Okay. So then g has a relative what there? Max of, did we find that? Oh, I'll fill in the blank later. At x equals 2, because g prime changes positive to negative at x equals 2. Now, just reminding you of language. If it says find all relative extrema, that means you have to find the y value. They will specifically say at what values of x does it occur if they're just asking for the x value. So I need to actually calculate what g of 2 is. Okay, so g of 2 is equal to the integral from 1 to 2 of the graph of f. And what is that? 1/2. Good? All right, so this is a good review of all those old things because those are not going away. All right, now find the absolute extrema. Okay, so the absolute extrema, what test do we use? It's called the candidates test. And what are our candidates?
Endpoint.
The endpoints
and the
and the critical numbers. Well, we've already talked about the critical numbers in part C. So our critical number is at 2. So we know that, and we already know that value, so that's nice. So we're going to make our candidates test with a table of values. So we have x and g of x. Our endpoints are 0 and 4, and our critical value was at 2. We already calculated g of 0 from the very beginning, so we know that that's -3/2. We've already calculated g of 2, which is 1/2, so now we just have to calculate g of 4. I'll let you do that. You should get 1/2 minus pi. All right, we already know the integral from 1 to 2 is 1/2, and then you're subtracting 1/4 of that circle. 1/2 minus pi. So you can ballpark that in your head, right? 0.5 minus 3.14. It's going to be quite negative, right? It's bigger negative than -3/2. Okay, so 1/2 minus pi is your absolute min. And if I had more space and time, if you were doing this on an actual test, you would write that out. You would say g of x has an absolute minimum at -1/2. Okay, you'd say all that. And then absolute max at 1/2. All right, so now inflection points. For inflection points, we need to look at the second derivative. Yeah, okay, the second derivative. And Rafael, you're right. We're looking at like increasing and decreasing basically. So let's go ahead and do that. So if g prime equals f, then g double prime is equal to f prime. Okay, so we have, so again, I'm going to justify first. We have a point of inflection when g prime, which equals, sorry, g double prime, which equals f prime, changes sign. Another way you could say that, as Rafael was saying, is when, or, either of these are actually okay, or when g prime, which equals f, changes increasing to decreasing, or vice versa. Does that make sense? Either of those you could use. Okay, so f is always decreasing. You see that? We're always going down. All right, so since f is always decreasing, come on. Since f, which equals g prime, is always decreasing, there is no point of inflection.
Can you also say that f prime is always negative?
Yeah. Good? Okay, just reviewing all those old topics, but applying them to the new way of defining function. Okay? All right, so last little piece, this won't take very long. This will be especially helpful in those first few problems on the problem set when we're talking about velocity, position, velocity, and acceleration. All right, so a particle, if we're moving along an x-axis, this is something that you see a lot. So you're just looking at left and right distance when they say that, when you're looking at the x-axis. Where x is measured in feet and time is measured in seconds. V of t represents velocity, a of t represents acceleration, which is what do the following integrals represent. Okay, so this is one where, remember I walked it out for you, right? If this is in the center of the room, I start walking in this direction with positive velocity, and then I start walking this direction with negative velocity. I started here, but let's say I walk a little bit past, right? My total distance was like the total accumulation, right? Remember how much my Fitbit is accumulating. But my actual net distance, if I started here and ended here, okay, that's like -2 feet, okay? So that's what the integral represents. It represents the change in position because it takes into account your positive velocity, your negative velocity, the direction that you go. Okay, so it's very, very important that you understand the difference between the integral of velocity and the integral of speed. Because what's speed represented by? Speed, the speed function is the absolute value of the velocity. Speed is just magnitude, not direction. Okay, so the integral from 0 to 5 is, let's just show you, let's break it down. Correct, it's displacement. So velocity, if we use x as our position function, then velocity is the derivative of x, right? So using the fundamental theorem of calculus, that would be x of 5 minus x of 0. And then if you just read that statement, it's the change in position from 0 to 5, right? It's how much my distance changed. Okay, so this is change in position. So whenever you're interpreting an integral, it's always best to say change in whatever what you're accumulating from t equals 0 to t equals 5. So again, if I walked this, if I started here, walk over here a little bit, walk over here a little bit, and then up here, my change of position was -2. And it has a negative because it means I'm to the left of where I started. Does that make sense? Okay, and then if I walked over here, I'm to the right. But the actual distance that I traveled was more than 2 feet, right? Okay, if I walk 6 this way, I walk -6 this way, and plus a -2, I actually walked, what, is that 14 feet? Does that make sense? That's what this is represented by. All right, so this, if you're taking the absolute value, is the total distance traveled. So what you're going to have to do on the problem set, if I think on the problem set I ask you for this, which is easy to calculate, but this one's a little bit more difficult to calculate. So on the 2.5 problem set, on those first 3 questions, I ask you several different questions. Part A is asking for when the particle is moving to the left. I did that on purpose. Why? Oh, that's the right.
You can find that distance.
Right. This is finding when I have negative velocity. Okay. So, and it's actually also finding when you have positive velocity would be the other part of that interval. And so what's that doing? In part B, I'm asking for this, your displacement. In part C, I'm asking for this. Okay, I'm asking for the total distance traveled. So in finding that absolute value, we did a problem like this on a previous notes where you have to split this up into the positive piece and the negative piece. Does that make sense? Okay, you find the positive piece integral, and then you have to negate the negative piece. Okay? Yes?
Wait, never mind.
Okay. All right. Now, and for acceleration, similar to what we just did at the top, if you rewrite acceleration as the derivative of velocity, then this is equal to v of 5 minus v of 0, and that's the change in velocity from time 0 to 5.